Welcome back to Advent of Code 2019, day 22, final 4 days before Christmas Day. All right. So yesterday, well, not yesterday, but last day, we had this int code problem, which I gave up on because I just wasn't enjoying it. And I explained why during that video. So anyway, we've got a fresh start. This one won't be an int code one. Alright, let's see what it is. Slam shuffle. There isn't much to do while you wait for the droids to repair your ship. At least you're drifting in the right direction. You decide to practice a new card shuffle you've been working on. Digging through the ship's storage, you find a deck of space cards. Just like any deck of space cards, there are 10,007 cards in the deck, of course, numbered 0 through 10,006. The deck must be new. They're still in factory order. With 0 on the top. Okay. You've been practicing 3 different techniques that you use while shuffling. Suppose you have a deck of only 10 cards. To deal into a new stack, create a new stack of cards by dealing the top card of the deck onto the top of the new stack repeatedly until you run out of cards. Yeah. So kind of just reversing what you're holding on to. Pick up the new stack you've just created and use it as the deck for the next technique. So is it not just reversing the whatever the deck is? Load the edge A to the new stack. Create a new stack by dealing the top card of the deck onto the top of the new stack. So then that becomes the new deck. So you're actually just reversing the current deck. Okay. Fine. To cut N cards, take the top N cards off the top of the deck and move them as a single unit to the bottom of the deck, retaining their order. Okay. To cut 3, you put... Okay, fine. I just realized factorial notation just makes me look excited about 10,007 cards. Okay, so cut is just... Okay, move. Oh, you've got negative cut as well. But that's just the same as... So cut -4, but that's just the same as cut 6, right? You would take those 6 and put them in the end. So cut -4 is the same as cut 6. Alright. So that's cut, and then deal with increment N. Start by clearing enough space on your table to lay out all of the cards individually in a long line. Okay. Deal the top card onto the leftmost position. Then move N positions to the right and deal the next card there. If you would move into a position past the end of the space on the table, wrap around. Okay, fine. So you increase... So you just put it at intervals N in a wraparound. You just have to deal with increment 3. So if So if the increment is co-prime to the number of the size of your deck, then this process will actually fill all the spaces without duplicating. You won't end up trying to put like another card on top of one. If they're co-prime, there's no common factors, so you will end up just visiting every space, I think. If they're both prime, that's definitely true. If they're co-prime, I think that's also true. So I assume they're only ever going to give us... Well, if they give us n, a prime number n, I'm guessing they do, then it's always going to be co-prime, isn't it? They might... I don't know, they might have chosen the numbers nicely. Positions on the table which already contain cards are still counted. They're not skipped. Oh. Okay, no. Wait, so... This technique is carefully designed so it will never put two cards in the same position or leave a position empty. In other words, they're giving us co-prime numbers. Alright, fine. Finally, collect the cards on the table so that the leftmost card ends up at the top of your deck. Either Twitch or your internet is being sort of bad. Did it disconnect again? Hang on. Oh, really? That's weird. OBS didn't say anything. Okay. Yeah, it looks like it did. I can see in Discord, but OBS didn't mention anything. Alright. So we have these three techniques. I'm guessing part one will be quite easy. We just implement those as a simulation, and then part two is going to be something more difficult, isn't it? Collect the cards on the table so that the leftmost card ends up at top. Card to its right. Okay, fine. The complete shuffle process consists of applying many of these techniques. Here are some examples that combine techniques. They all start with a factory order deck of 10 cards. Okay. Yeah. Alright. Positions within the deck count from 0 at the top. Fine. Blah, blah, blah. So we've got 10,000 cards. So, in theory, every one of these types of shuffles could take at most 10,000 steps, linear time, if we're doing it the slow way. So it's basically 10,000 times the number of these lines, which is fine. We could simulate that for part one at least. Okay. Alright, let's just do that then. It's in plain words, so we need to interpret this, okay. So let's just have a look at, I don't know, 20, copy some scripts. Okay, do it like this. What do we... we'll just read, we'll just do it as we read each line. So... let's say... Okay. So we've got a deck, which is going to be list range 10,007. That's the initial deck. Oh, I think I disconnected again. What's going on? No, it just slowed down a bit. Alright, I just grabbed my coffee. Alright, I missed this stream. I might just do part 1, I'm not sure. Depends how long I'll... Internet cannot handle the bitrate demands of coding. I think we'll just make these as 3 separate methods. So let's say... define... new stack, deal... Hang on, so new stack. Okay, fine, new stack is one command. But that's... just this. Reverse it. Should we return a new deck or just change it in place? Or return a new deck. Might want to change that later on if we're trying to save time. Because there are more efficient ways of cutting. Okay. So that's just literally just reverse the deck. Cut. So if we cut with a number, well, so let's define n to be 10,007. I have a feeling they might give us a bigger number next time for part 2. Okay, so for amount C, so if it's negative, we actually want n plus C and then modded. So either way, we can just do this. N plus C send n. That's the cut amount. Because if C is positive, it will just become C. And if C is negative, it will become n minus C. Well, n plus C, because C is negative. So it'll be n minus some positive amount. So we just do this, return the cut amount plus onwards like that. Okay. And then finally increment. Increment. Okay, so in this one we we could just make an array. With nuns in it. And then for k in range n. The first one goes at 0, the next one goes at I along. So it's going to be k times I percent n. That's the position we insert it in. Then we return this new array. So those are the 3 operations. Each takes linear time. There might be ways to do that faster when we want to speed it up. So we want alright, split this into tokens. So tokens equals so the amount will be the last token, regardless of what we're doing. Unless it's new stack. Oh no, wait. Okay, hang on. No. Alright. If let's just do each. Okay, so if tokens 0 is cut, then so the deck, we've already got the deck. Okay, let's just move this down. Deck equals cut deck okay elif tokens. So otherwise, if it's with, so it's similar, but we do increment. We don't need to check the last case, but do it anyway. Into. equals new stack. Alright. And then what? What is the position of card 2019? Alright. Run it. 3844. Too low. Position. As in... Okay. Okay. We might need to try one of these test cases then, so... Let's try this last one. So this was for a deck of size... 10. So 2019 is not on the list. So 9258147 036. That's correct. Let's just try these other ones then. Oh 74. That's wrong. Okay, good. What has happened? So it should be 6307. How did we get the last one to... succeed? Maybe it's into new stack that we're doing wrong. Am I understanding into new stack correctly? Because that's the one that's confusing me. Deal the top card of the deck onto the top of the new stack repeatedly until you run out of cards. It is just reversing the deck, isn't it? Yeah. So this failed, but the last one passed, even though it was more complex, and that had into new stack in. This one, okay, so it's probably an issue with... Well, that's really weird. All right, fine. Let's just print the deck at every step. Okay. Oh, why is it not changing here? Take that out. Alright, so that's the first deck. And then we apply deal with increment 7. It looks like the final step is not working. Cut -2. Should I just put the line in so we can see what happens? So cut -2, we still get the same thing. That's the problem there. Why has that happened? -2. So it should be... Maybe I've not done the arithmetic correctly. Oh! Ah, it should be -1 if it's negative. Hang on. So if we've got -1, cut -1, we want the cut amount to be... size of the array n. -1. No, that's fine. Also, let's not call it cut amount, call it cut index. Cut index equals... print cut index 8. 1, 2, 3, 4, 5, 6, 7, 8. Oh my god! I've got this the wrong way around. This is just D. This is just D up to that point, plus D from that point onwards. So... how did I get it right for that more complex example then? They must have just had a symmetry in there. (6307). They had cut -2, cut -4, cut 3, cut -1. How did that work out? Alright, fine, whatever. Don't want to know. It's just... okay, so... (7395). Okay, it's higher. Correct. After a while, you realize your shuffling skill won't improve much more with merely a single deck of cards. You ask every 3D printer on the ship to make you some more cards while you check on the ship repairs. While reviewing the work the droids have finished so far, you think you see Halley's Comet fly past. Halley's Comet. Have I ever seen Halley's Comet? Remember the last time? No, I haven't. In 1986, and will next appear in mid-2061. So we've still got about 40 years to go. Okay. I will make a note somewhere. Alright, when you get back, you discover that the 3D printers have combined their power to create for you a single giant brand new factory order deck of this many space cards. Wonderful. Finally, a deck of cards worthy of shuffling. You decide to apply your complete shuffle process to the deck that many times in a row. What? Okay. You'll need to be careful though. One wrong move with this many cards and you might overflow your entire ship. After shuffling your new giant... What the heck is this? Twitch scam U19. Not suspicious at all. Long live chaos, something something, scam, fix match, hello. Open your tap every evening to bleach to... Okay. Thank you for that. Is that... What is that even a scam? What is... No link or anything. Okay. How the heck are we gonna do this? What? Okay, so we only care about whatever ends up in position 2020. Position 2020. So this time we're not following the specific card around. We just want to see what ends up in position 2020. So obviously we can't just do this many times, but if we did, we would just care about what ends up. Okay. This whole process corresponds to a permutation. So once we know what that permutation is, even though it's for this many cards, we can work out what the permutation is without actually shuffling the cards around. Can we? Well, sort of. Not really. Not fully. But we can figure out where certain cards... We can follow certain cards around by that process. Hello, Toucan Tom. Damn, 101 trillion times in a row, I'd say it would be well shuffled by then. You would think, but... Maybe. So what do they say for a deck of 52 cards? If you do a riffle shuffle like 7 times, roughly, it's pretty much random. Although this isn't random. This is actually deterministic, so I guess by definition this is not even a shuffle. Because there's no randomness. Alright, so what do we want to do here? I think we want to figure out Oh, I've disconnected again. And we're back. That was a very brief disconnection. Okay, so I think what we're gonna do is just follow the card 2020 around in this shuffle, see where it goes, figure out its pattern. Once we know that, then we know, regardless of whatever else is going on in the deck, the positions it goes to, those cards, let's say it goes to 20 different positions and then returns back to its starting point. Those 20 cards are just cycling round in a circle trillions of times. It may not be 20 cards, it may be 100, it may be 1,000, I don't know. But hopefully some small number. So if we could just identify that cycle of cards, then we're pretty much done, aren't we? We can work out, even for these trillions, we can use modular arithmetic to work out which of the cycle which part of the cycle will be in. All right, let's try and get some numbers here. So yeah, but the thing is, to do this, we do need to know okay. So basically, the first step I would say is just focus on a certain card, 2020, and rewrite our shuffling method so it only follows where 2020 will go, and not the other things, essentially. And then just what will be the next step be? I'm not entirely sure. All right, so I think let's just get a list of indices of where 2020 ends up. Then we'll worry about everything else later. So let's say n equals, so this is part 2 now. Okay, so n equals that number there. So let's say new stack. Okay, we no longer are configuring a deck around. We just want to know where a given index I, whatever card is at I, we want to know where it'll end up after performing a new stack operation. Okay. This one should be easy, right? It's just return n minus I minus 1. Yeah. I think. Okay. Cut. We could actually run this on part 1. We should be able to figure out where 2000 and... What was the question for part 1? Find out where 2019 ends up. Yes, exactly. We can actually do this for part 1. And in which case we could just get rid of all these previous methods. This is actually the superior way to go. Alright, so... We don't... Okay, so... Cut index equals that. Yeah. So... If I was greater or equal to cut index, then it's going to come to the front, essentially. So it's going to come forward. So return I minus cut index. For example, if I was exactly cut index, we take the front cards and put them at the end. So now you become position 0. And then everything else falls. So you subtract that many cards. All right. Else, it's in the left half. That means it goes to the end. So whatever number of cards is after us, we add. So it's going to be whatever it was before plus. So it's going to be return I plus n minus, so like this. Cut index. Is that right? So if we are at the front, and we're cutting, say, I don't know, 3, then the number of cards on the right hand side are n minus 3. They go in front. So it'll be n minus 3 plus 0. I think that's right. Okay. All right, so that's cut, and then increment. Increment might be the tricky one. So no, increment's the easy one. So we have this array. Oh, no, wait, hang on. No, this is the hard one, but it's not that hard. We need to use one of these theorems, Fermat's last theorem or something. So we don't care about... We want to find the position where this is J. We want to find... So this is I. We want to find the... Oh, no, we don't need to use Fermat's last theorem. So we want to find... So when we get to, say, 2020, we know where we're going to put 2020. It's going to go here. So it's literally... It's just this, isn't it? Oops. It's just... Return that. Where that's up. So let's call that ink. That's the ink amount. And we want the index where we end up. It's going to be ink times I percent n. Yeah, it's just that, isn't it? Alright, so we can now test this by running this again, but there's no deck. And we just want to find out where 2000... So for part 1... we want to... Okay, so index equals... So for part 1, our index was 2019. We want to keep track of that, where that index goes. So we do, if it's cut, we do index equals, we replace it with cut of the amount and our past index to get the new index. Increment, we do the same. We say okay. Then afterwards we just print index. So this should hopefully tell us where 2019 has ended up after this whole process. (7395, 7395). Yes, the same as before. Okay. Okay. So we've improved part 1. Now no more. Okay, get rid of these methods. We don't need a deck. We can follow a single card around. Get rid of this. Leave that out for now. So 7395. So for this big old number, we can work out where 2020 ends up after 1 shuffle. And there's no reason it would take any longer, right? There, that's where it should end up after 1 shuffle. So we can wrap this up. Let's say define shuffle for given index. So we just want to work out where a certain card goes after 1 full shuffle, because this is like an atomic operation. There's no reason to split this up. So here we can just plop all this in. All right. So here is shuffle 2020. Hang on, I got a different number. Index equals 2020. Ah, no, index and I. There we go. Okay. So just move all this stuff around. So put these at the top. Okay. So this is the two parts, right? So for 2019, let's just make sure we're still getting the right answer. 7395. Correct. Okay. Okay, so now the thing is we need to work out what the full sequence of indices 2020 follows until it returns to the start. And in theory, this could go the full length of the number, but in practice, I don't think it will. They've probably chosen the numbers that it's nice. So how do we do that? Cycle equals. So the first position it starts at is 2020. We just want a full list of all the places it's been. So while true, index equals shuffle index. If index equals 2020, so let's say initial index equals 2020. So if we reach the initial one, then break out of this loop. Otherwise, just pop it on the cycle. So if, I hope this actually... How big is this cycle? Taking a while. It definitely terminates, but it could terminate anywhere from a small number to that massive number, and that massive number is too massive, so I don't know what we're gonna get here. We can use exponentiation to, like, if we take a cycle and multiply it by itself, we get that cycle squared. We do that again, we get the cycle squared again. So you can without too much difficulty, you can create so I can quite easily find out where 2020 ends up after that many cycles using exponentiation. But that's not what we're looking for. We're looking for what ends up at position 2020. So wait, does that mean we just do a reverse shuffle? So we need to find the inverse of this entire shuffle. And just apply that? Wait, no. What am I trying to do? Yes. Isn't that it? So we have the ability to find out where an index ends up after applying this shuffle any number of times. So, but we're trying to find out what ends up at this place, not where this card ends up. So we can just do the opposite. We can just say, okay, this card is here at 2020. Where does it end up if we do the shuffle backwards? Isn't that the right answer? Wouldn't that give us the exact same answer? Oh man, this is group theory. It's interesting stuff. I was quite interested in group theory back when I studied it. But yeah, it's like, it involves all these symmetries and permutations and combinatorics and stuff like this. I think, based on what I remember, that is actually the case, right? It's a permutation is invertible. It forms a group. So every permutation has inverse. Okay, so every permutation is also a product of cycles. So stop this. So things do Alright, I think we want to work out what the inverse shuffle is. So if we know what the shuffle is, we can just do every step backwards, I suppose. I mean, you can also just take your permutation and well, let's try this. Inverted shuffle. So we go backwards. Or we can say, I don't know, reversed. I have to upgrade lines. So we do this as normal. So if it was cut. No, wait. So if the operation was cut a certain amount, then what we actually want to do is the opposite, which is cut of n minus that amount, right? Wait, don't we just isn't it just negative the number? So if it's... Yeah, it is negative the number. Oh, and I don't have my code visible, do I? No, I do. What's up with the... Why is it all glitched? There we go. It's... Yes, okay. So we do negative I here. Okay, so that's that. Increment. How do we invert increment? So, okay, into is easy. It's the same. It's self-inverted. It's self-invertible, so we don't need to do anything for that. So for increment, what is the inverse of increment? So we're inverting this function here. I maps to inc times I. So how do we go backwards? Oh, this is where you have to use Fermat's theorem or something. So it's like... to go... this function was basically multiplying I by inc. If we want to go backwards, we need to multiply by the inverse of inc. We need to find the inverse using Fermat's theorem or whatever. Let's see. Multiplicative inverse, here we are. Aha. This is what we're trying to do here. When m is prime, I assume we're dealing with prime numbers, modular inverse is given by this, so it's a to the m minus 2 mod m. So inc is our a. So it's erasing inc. To the power of hang on, so inc equals this. So basically we want to do inc raise inc to the power of n minus 2 modulo n. Does it do modular exponentiation though? Or do I have to implement that myself? Because this will be too slow otherwise. Let's see. Oh. Doesn't really say, but it says more efficient algorithm, so I'm hoping it does. It should, because there's no reason not to. Okay, so inv inc equals that. So what are we doing? We're actually raising by the inv inc. So is that it? We can test this all out now, so we can say, all right, let's move this. Okay, go back to part 1. So, index is that. Okay, so J equals 1 shuffle index print J and then print inv shuffle of J. Hopefully we get 2019 again. Fuck. So, no. Why is that there? Get rid of that. Four, 5, 8, 5. It should. We're expecting to see 2019 again. This shouldn't be too hard to get right. There's probably a small error somewhere. Because I mean, this is not that complicated. So just going backwards through the f.read lines. And we're doing each step the inverse of the step. So if we cut with a certain number, so if we cut with 1, to do the backwards step we would do -1. Is that right? I think so. Yeah. It should just be... Oh, I put the minus in the wrong place. That's weird. That... was meaningless. Like, what did that even mean? Okay. That probably was the issue. Yes! Okay, okay. We haven't solved the problem yet, but we now have an inverse of the shuffle. We got 2019 back. So we now know how to shuffle backwards. So now, do we just shuffle 2020 backwards this many times? I feel my gut tells me that's all we need to do. All we need to do. We need to use exponentiation though, because we can't do it that many times. Oh no, we're not doing it that many times. We're doing it I didn't copy it in. Oops. There. That many times. Okay, so take that out. That in. That many times. So basically, we know how to shuffle once. Hang on, let's just... Okay, part 1. Just make sure we're... Part 1. N is this. Index is this. Print. Shuffle. Index, that's it. Okay. Get rid of this. Part 2. this. Does this still work? 7.95. Okay. I forget how to do this now. So how big is this number? Thousands, millions, billions. Yeah, obviously we can't. Okay, so how do I do exponentiation again? So we want to say define shuffle. No, don't call it shuffle. Wait, shuff. Call it shuff. So we want to do it k times applied to given index. All right. If k is 0, I don't know if this case will come up, but let's just say if it is, then we return I, doesn't move. If k is 1, okay, let's just say in shuffle, just so we know we're doing it backwards. K equals 1, we return 1. Go shuffle, okay. So otherwise, if it's a big number, what do? We split it into... We want to find the biggest power of 2. I'm gonna have to Google this. I know there's a process that you normally follow here. I just forget what it is. Exponentiation by squaring. I forgot to mention by squaring. That's the key here. Okay. All right, I think so if n was even, if k was even, if k is sent to 0, so k is even, then we want to do we're basically doing inv shuff k. I'm just writing this out what it would look like. I, and then we want to do inv shuff k over 2, like that, right? But that's not efficient because we're doing... I think we want to memorize this. But that's right. So no, hang on. No. This is not right. It is, but where are we getting the benefit? What's the benefit of splitting up this way? I think if we already knew how to do k over 2, then we would only have to do it once. But the problem is we've got a different index here, so this wouldn't actually speed it up. We can try and memorize it and see if that helps, otherwise I need to think a bit smarter here. So otherwise, k is odd. So we should just do this, say inverse k minus 1 I, and then whatever we get for that, we do one more shuffle, right? Inv shuff 1. And that. So that is correct. It's just I don't know if I've actually sped it up correctly. Okay, let's try it without memorization. Let's just see if it actually does anything. So we want to... The ultimate answer is... inverse shuffle. That many times... I'll give an index. Well, this. Alright, I suspect this will take too long, but that's probably where we need memorization. Because this is not actually speeding up anything, it's just doing every step as before. Okay, now try memorization. Keep forgetting how to do this. Okay, why can't I find it? I'm trying to find the built-in thingy that... What's it called? Cache? Memorization, cache... Decorator... I can't even type. No, I just see a million guides on how to write your own. I don't want to write my own. Funk Tools at Cash, thank you. Okay. Alright, try now. It's still going to be too slow. What am I missing here? I need to... find a way to... turn this into one operation instead of two, isn't it? I think we actually have to go back to this inverse shuffle and break it down a bit further, because all it does, this method, all it does is spit out a given index, but that doesn't give us the ability to square it. To actually square something, we need to be able to get the full... oh man, I'm not sure what to... I think... I'm not sure. The thing we want to square is basically the entire shuffle, but we don't have the whole shuffle, and we can't because it's a huge number. But we want to be able to square it, which we can't just do it for one index, because then we haven't really got what we need, have we? It must be close, though. Like, we've got that, and we know we want to do that a lot of times. Let me turn the AC off. I need to think about this offline. This is some group theory stuff. Again, this is advanced stuff. This is not... I mean, this is university level mathematics. You don't... I did a bit of groups in school, but not even to this extent. Like using Fermat's theorem and everything. Which we've done to get the inverted shuffle. Now the last step, and it's probably just a small step that I'm missing. How do I get the square of a permutation without having to compute the whole thing? I want to be able to say... I want to do inverted shuffle 2 to the power of, I don't know, 20 times applied to a single index. How do I get that result? If I knew how to do it 2 to the power 10 times, what simple step could I do to get to 2020? Right now I can't do that because it would use a different index each time. If I knew the full shuffle, then I would. I could just apply... I mean, if I were to transform... I'm sure I've solved problems like this before, back when I was in school, university even. It's probably like a warm-up question as well, for group theory. It's not even complicated, it's just, I can't remember this stuff. And 2019, this was a pretty specialized year. I saw people mentioning that it really peaked in terms of advanced knowledge needed. Inverse shuffle. We got as far as getting an inverse shuffle. That's a good first step. I know it's something like what I've done here. It all falls apart at this line here. This is 2 operations instead of 1, so it just goes back to being linear. If I could make this 1 operation, then we're done. What am I missing here? What we really want is not take out this I. What we really want is inverse shuffle k times. No index. We just want to be able to... Oh my God. But we only know how to do it for 1 index. If we do it for the whole thing... I might have to think about this offline then. Could we just write this shuffle as a product of groups? Even though n is huge, we might be able to describe the shuffle in a small amount of cycles simply because of the way these instructions work. I think that might actually be true. Oh, but I don't remember any of this stuff. So to start with is the identity. And every time we do a cut, I don't like this. Alright, that was only 1.5 hours spent, so not bad so far. I'll put in some work offline and see if I can figure it out. Open Paint, which I should have done before the stream, but... Okay, so we've got... Paint open. Okay. So, what we've got is a permutation, a shuffle of the deck. And we know we're able to work out where a given element goes. Okay. Which is good. But... So at this point we don't care much about the nature of the permutation, we're just able to calculate where a given element goes. But that was my mistake, slightly. There is still some more information about the nature of this permutation which matters here. Okay. So, if we think about it, if we have a... So we have a permutation, right? Which maps x to, like, p of x, right? And we're able to compute that for a given x. But we can't really do it many, many times. But if we look at all the individual operations of this shuffle, there are 3 types, right? So there's the reverse, that's the simple one. But that's almost like negative. Or it's like... So when you reverse the deck, you're kind of doing x to... it's like n minus x plus 1 or something like that. I don't know. Then there might be a plus 1, minus 1. Doesn't matter. If you do the cut, then it's almost as if you're just doing x plus the cut factor, right? Mod n. Everything's mod n. Even here, but in the reverse it doesn't matter. So it's like you're just adding something. And if you do the what was the other one? The other one, then what was it called? Increment. No. Yeah, increment. Then it kind of, you're kind of multiplying. So if you do increment k, it's essentially k x mod n. Alright. So if you look at these, they're all linear functions. So if you do any combination of these, any number of times, it all equates to some linear function, x to a x plus b. Like, you could just compute the a's and the b's for every operation to get the final a and b, or we could just do it and find out what the a's and b's afterwards, because now that we know x maps to ax plus b for some fixed values of a and b, we can just work out a and b. So if we set x to be 0, see where 0 maps to, then that'll immediately get us what b is, because the a is irrelevant. So we could do that. We're doing this for the inverse shuffle, and then for x equals 1, we could. All right, let's try and do that, and then we'll see if it works, so we can then test it. So instead of doing that whole shuffle, we would then be able to just do ax plus b to find out what the result of the shuffle is, instead of doing the shuffle. And so the input is no longer relevant, and we've got a very simple way to apply the function. Okay. So let's see. So here we don't need func tools right now. Turn that on. So this is our inverse shuffle. What was K and I? Alright, this is inverse shuffle once. Okay, you know what? We don't need this thing. We can take that out. That was an attempt to do a multi shuffle. Doing a shuffle n times. Alright, so we know how to do one inverse shuffle. We want to find the A and B. So f, so let's just write a comment here. F of x equals ax plus b. Alright. Compute b. So we do so if we do inverse shuffle, Inverse shuffle of 0. Would that just give us B then? Yeah. It will, won't it? It's doing... Alright, try that. Inverse shuffle. It's using the N. Okay, try that. B is that. Now what's A? Is that within... Yeah, it is. Okay, so now we want A. So we just want to do... So if we do inverse shuffle of 1, that would be A plus B. So then subtract B, that would be A, right? Okay, so we've got A and B. Now let's test this theory. So we do inverse shuffle of, let's pick some number, 67. And print A times 67 plus B mod. Well, you don't really need to do the mod, but we can do it. And they should be the same. But you do need to do the mod, sorry. Yes! Okay, we're getting somewhere. So that means now we never need to call this method again. We now know how to do this quickly. Alright, what now? So now we're trying to apply this inverse shuffle, which is now just AX plus B. We're trying to do it this many times. Okay. So... It's AX plus B. Let me bring the paint out again. So, if you apply the function once, it's going to be AX plus B. If you apply the function twice, it'll be... So you'd have to multiply out this, so you'd get A squared X plus AB plus B. I'm just looking at the pattern here. If you did it 3 times, you'd have to do A cubed X plus A squared B plus A, B plus B. Okay, so the general case is A to the K X plus, and then you got B multiplied by, so it's going to be all the way from A to the 0 plus A to the 1 plus dot 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 plus A to the K minus 1. That's geometric progression. So that's 8. I don't remember. What was the formula for this? Is it A to the K minus 1 over A minus 1? I actually don't remember. I'm just going to look this up just to make sure I got it right. Sum of geometric series. So r to the 0 plus r to the 1 plus dot 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 plus r to the n minus 1 equals 1, says r to the n minus 1 over r minus 1. Yeah. And this is A. That's it. Okay, fine. So that is the final. Okay. X plus B. So that's constant time. Computable. Wait, no. To do exponentiation, we're gonna have to. But Python has a power method for the exponentiation, so I'm pretty sure it can just do it. So this is the formula. The only catch is doing a to the power of k for a big value of k. You need to use modular exponentiation, but Python has that built in, so you don't have to write it yourself. I think other languages you probably would. Okay. Just write that down. A to the k x plus b a to the k minus 1 over a minus 1. But I mean, we're basically there now, aren't we? We're just applying 2020 bx here, so. So once we've got that, so let's compute the BA bit. All right, so we got, just say temp equals but wait, when it's modular, how do you divide by a minus 1 here? Because that's not, you can't divide. Oh, I forget. So you have to find them. Find the modular inverse of a minus 1. Okay. N is a prime, so every element has a modular inverse. But I forget all this stuff. Is this where you use... Oh, you use Euler's theorem. Oh. When m is prime, it's just... Oh, we already did this earlier, didn't we? A to the m minus 2 mod s. So it's a to the n minus 2. Okay. So... So the modular... So... Modular inverse of a minus 1. That's what we want. Let's call it t, I don't know. T equals... So it's going to be... a minus 1 to the n minus 2 mod n. Okay. That gets us that. So we want a. So we want power a to the power of 2020. So index. No, not index. To the power of num, which is that. Num. N. Minus 1. It could become negative, so we've got to do this. And then times the inverse of a minus 1, so that's going to be t. Should we just do these as a series of steps, otherwise it's going to look horrible. So let's just, hang on, just do temp equals power of a to the num t minus 1% n. Okay, that's the first step. And then we do temp equals, so it's going to be temp times t, the modular inverse of a minus 1, percent n, okay. Then we multiply by b, temp equals temp times b, percent n. And then finally we do temp equals, it's going to be temp plus power of a to the power num n. So that again, which we've computed once already, times index 2020. Percent n. Is that it? Print temp? So POW should just do this efficiently. Debug. Is that it? The result? It's easy to get this wrong if we've got the formula. Oh, that's it. So the key, I was pretty close last time. The key step that I missed, and I did look up a hint for this, just a very vague hint. The vague hint was that this permutation is linear. That was pretty much it. It clicked once I read that. But that is an important lesson. Always keep an eye out for linearity, because when something's linear, especially in these advent of code problems, that's usually a clue. Because linear, that's the goal of mathematics, isn't it? Make everything linear. We want everything to be linear. And if anything's non-linear, we try to make it linear. That's just like the one lesson I remember the most from university level mathematics. We want everything to be linear. But once it's linear, you don't even need to compute the coefficients. You just compute the permutation. You can get the coefficients from the result pretty easily. Modular inverse. Use Euler's theorem to get the modular inverse. That's something I didn't remember. I mean, it's still pretty specialized. That's going to be quite hard for anyone who's not studied group theory, permutation theory, combinatorics, just any, even number theory for the modular inverse and stuff like that, or cryptography. So people would get stuck and they wouldn't even know what to look up or what to learn more about in order to get to the answer. So I can imagine that would happen to some people, but it was okay. It was actually a pretty good problem. Specialized problem, but a pretty good one. I'll have to keep in mind. I don't think he'll put problems like that again, but maybe. So you can't really glean anything from these stats here. It's a bit tricky to... So yeah, fewer people comparatively compared to all these problems here. Relatively few people actually did part 2. You can see that. Okay. And for the next problem, the ratio is very high for solving part 2, so that indicates it's probably an easy problem. We can take a sneak peek now. I'm not going to do it now. Yeah, that was a nice refresher of group theory, which I didn't like. So I probably would have been able to solve this after my first year of undergraduate mathematics, but probably not using my high school level mathematics. I did actually do group theory in high school, but it's probably not solid enough to be able to... I wouldn't know how to do the modular inverse of... I probably would have got stuck as far as how to compute a to the k minus 1 over a minus 1, which is actually the easiest part, but I wouldn't really have known how to use Euler's method for that. But everything else, I probably would have... I knew about permutations and stuff, and the geometric sum of sequence. Yes, the number theory aspect I didn't study in school. yeah, I mean, in group theory, in algebra, in mathematics, that would have been a warm-up question. It wouldn't have even been an exam question. It would be too simple for an exam question. This would be like, this is the kind of question to be a warm-up that just shows how out of date I am with all the stuff I studied, but yeah. Looks like Warza and First have done all the problems. Alright, so tomorrow, next days will be day 23. So what were the times? I'm curious about, I think the times will be pretty quick for this. Because once you know what you're doing, you can pretty quickly, if you're a pro at these problems, you can pretty quickly assume it's going to be linear. Because they always are, if it's solvable. So then you can just churn out a solution pretty quickly if you knew that. It's just that formula that I wrote at the end. So I'm guessing the times are really quick, maybe like 10 to 20 minutes. What was it? 22. Hello, Olympus Tiger. Two hours. Is this the same problem? 2 hours. Yeah, it is. Wow, that's way longer than I thought it would take. Because once you've got the you did day 22 a couple of days ago. How did you find it? It's the longest to leaderboard. I'm pretty proud of it. Yeah, it's... But I'm actually surprised it took them so long, because even though it is actually a specialized problem and quite difficult in terms of the mathematics, once you've got the formula, which is a classic formula, it's like... I've seen this formula so many times before. I'd have thought more people than that would just type in the formula, because my code, I mean, this is my code just looks like this basically. Oh, 2015, not 2019. I'm doing 2019. I don't know what 2015 is. I can look that up in a second. But yeah, it seems like I guess you do have to first do the shuffle, which is probably the longest bit, but it's not too bad. Once you've done that. Oh, the wizard fight one, I remember that. Like an RPG game. Once you've written, so this is the hardest bit, the inverse shuffle. But it's not that hard to write. Once you've done that, then the rest is just applying this formula. So that's super quick. I'm still surprised it took them 2 hours. Interesting. How long did it take me? This is my second stream. The first stream, I've got the video stored somewhere. (2022) part 1.5 hours. It took me 2 hours, and that's with a lot of waffling and talking and stuff. So actually, I would have been in the top 100, apparently. Okay. I'm guessing a lot of the people competing in that year didn't really know enough about algebra, because it is quite specialized. Okay. So yeah, part 1 was 12 minutes, so it took them another, like, 2 hours, basically, to do the part 2. Surprises me, but okay. The wizard fight one. So this was... ...2015. Day 22. Oh yeah. Was this the one that I kind of solved by hand before? Hand? Or... No. I think I had someone in chat trying to solve it by hand while I was coding it, and we sort of... I think he almost arrived at the answer by hand. And he isn't a coder or a mathematician or anything, he's just someone who plays a lot of RPG games, so he was using his experience of combat systems and stuff, which is quite cool. Yeah, that was a fun one. I use Dijkstra's, but there isn't a specific grid and ends with 4.5 mil items in queue. Oh, I don't really... So you're trying to find, what, the least amount of mana to win? Are there any choices, decisions you have to make, or is it just like... You hit, they hit, you hit, they hit? Oh, you do actually make choices of spells. Ah, so yeah. So you do need to have some sort of search. So you can't just... But do you do like binary search amongst the different amounts of manas then? Like for a given amount of mana, or so like given a amount of mana M, you then do a search, breadth first search, whatever, to Dijkstra to search to find a path which will kill them, and then go higher or lower for that M. I can't really remember what I did for this. So yeah, you're trying to basically find any path which gets the enemy to 0 health. That's the goal. Yeah, that's my guess for what I did. I don't remember, but I assume I would have just given a fixed mana, used a search to see if there's any path which leads to 0 on the enemy's part, and Dijkstra would, or A star even, would help cut out a lot of branches. And then just like halve the mana or double it or whatever, just to do binary search on the starting manas. I assume that's what I did. Oh, no, it's not the starting mana that changes. It's the amount you spend. Ah. But you could actually just alter the starting mana, because it's like that would force the amount you spend. Okay, cool. I just started 2023, so my knowledge on algorithms is not that great. My first year finished also. So you finished 2015 and you've moved on to the latest one? I can't remember how different they were to 2015. Did he have any assembly code problems in this one? in 2015, his first one, I think he was only expecting like 30 to 50 people taking part. And when he launched it, it was just spreading like wildfire, and he was getting thousands of people playing, and he had to increase his servers to keep up with it. Like, he only ever thought he'd have like 20, 30 people participate. He's got a talk. I think he did a talk at Google or something. Yeah, you saw that? Yeah, it's a good talk. He came in my chat once. He was watching me, Eric was watching me solve, I think, the sand problem in, I think, 2022 maybe. Yeah. Every now and then he stops in Twitch streamers' chats if they're doing problems, usually for the live ones. Okay, so... Oh, should we take a sneak peek of the next problem that I might do tomorrow? 23. I hope this is an easy one. I just want it to be easy. Oh, it's gonna be an int code. Don't know what this is about. It looks like just... On first glance, it looks like just some basic simulation where you just run your simulation. I don't see much in the way of algorithms here. At least... And apparently part 2 had a very high success rate for this, so... Okay, looks like an easy one. I guess I'll try and do that tomorrow. Yeah, I think people have said 2019 was like the hardest year, because this is where he started putting in some specialized things. Specialized mathematics, and he stopped doing that for the later years because it was kind of... I think in general people didn't like that because it was a bit too specialized. But... Alright. Alright. Well, thanks for stopping by, Olympus Tiger, and I might be back on tomorrow. If not tomorrow, then maybe the day after. Or probably a couple of hours earlier than I did today's session, if I can manage. Alright, see you next time. Bye-bye.